Look at a common party balloon. To our human eyes, the air inside seems entirely at rest. But that macroscopic stillness is a total fabrication. If you zoom in far enough, you find a violent, restless swarm of molecules. This chaotic motion is the foundation of the kinetic theory of matter. How does this microscopic bedlam result in the stable, predictable forces we rely on to keep tires inflated or planes in the air? The calm we perceive is actually a statistical byproduct, constructed by billions of non-stop collisions occurring every fraction of a second. To understand the physics, we have to look at a theoretical sandbox called an ideal gas. We strip away the complexities of the real world to see the pure mathematics at play. We start our simulation by programming a massively large population of particles. On the scale of Avogadro's number, we are dealing with roughly 600 billion trillion molecules for every 22 liters of space. Despite that massive crowd, these molecules are so small that a gas is actually composed almost entirely of empty space. At ordinary pressures, the average distance between any two gas molecules is more than 10 times the size of the molecule itself. Because they are so far apart, their mutual attractions are essentially zero. They move freely, indifferent to the other particles around them. In this void, every particle perfectly obeys Newton's first law of motion. Each molecule shoots across the container in a perfectly straight line, never curving or slowing down until it hits a boundary. While these particles do occasionally collide with each other, we are interested in the steady-state distribution of their speeds, the average activity of the whole group. The critical moment happens when a molecule strikes the solid, stationary walls of our container. We program these as elastic collisions. When a molecule hits the wall, no kinetic energy is lost. It is a perfect ricochet where total momentum is conserved. These straight lines and perfect bounces ensure that energy never drains out of the system. The gas remains in a state of dynamic equilibrium. Let's isolate a single particle on a collision course with the wall. Its velocity can be broken down into 3 components. The only one that creates pressure on this specific wall is the x component, the speed driving it forward. During the impact, the components of velocity parallel to the wall remain completely unchanged, but the x component perfectly reverses its sign. It goes in as positive v sub x, and it bounces back as negative v sub x. Since the momentum flips direction, the total momentum imparted to the wall is exactly 2 times the mass times that original forward velocity. This microscopic push is the essential building block of gas pressure. A single molecule's momentum transfer is virtually undetectable at the human scale. But when we move back to full speed, we see trillions of particles hitting that same wall every millisecond. We define macroscopic pressure as the total force, the combined rate of all those momentum transfers, divided by the surface area of the wall. As long as the volume and temperature are fixed, this drum roll of impacts remains steady and measurable. Pressure is not a static weight, but the statistical average of trillions of microscopic, elastic impacts occurring every second. The steady pressure we read on a gauge is the collective result of these individual mechanical collisions. The weight of a 2-ton car is suspended by the momentum of air molecules drumming against the inner walls of the tires at incredible speeds. To master the massive visible forces of our world, we must first program and understand the invisible mathematical chaos beneath them.